Okay, Professor Campillo, we can see your
Okay.
screen.
Yes.
Okay,
Just see the screen
it
now.
seems we're
Okay.
ready now.
So I can start. Finished. Yeah.
Can we start?
Yes. If you see the presentation, I can start.
Okay.
Thank you.
Okay.
Somebody has said to me.
Yeah, dear
Okay. Thank you.
everyone, I'm glad to announce the next speaker. It's Antonio Campillo, who's gonna talk about Laurent series and the Poincaré series. Professor Campillo, the floor is yours.
Okay. So thank you very much for the invitation. I'm very happy just to have the possibility to talk. And yes, sorry because I could not go to Moscow, but I expect all of you enjoy there and we from many places. Okay, so the relationship. So congratulations, Sabir. First of, uh, first of all, around 30 years, Sabir is working together with us in Spain, in Madrid and Valladolid mainly. And just here, we work together with um, make systematic research on Poincaré series with Felix Delgado. Sabir is coming every year. And so I wanted to thank Sabir just to all our aid. Of course, along those years, the topic of Poincaré series was also discussed with eventual visitors and collaborators of the department, and of course, students, former students of mine, for instance. And so today I wanted just to talk a little bit um, on some of the things which are not were not commonly discussed with Sabir, because are not developed. But I believe that there is still a lot of work, not only in the actual line of work, but maybe in others. So the ideas I will explain today, which are quite the explanation will be quite elementary, belongs to all those people related to the department, like for instance Dale Kutkowski and Anna Reguera, also Jürgen Herzog, which died last year, Mrs. Wade, and also Anne Lemayer, which is now in Nice, also Ricardo Podestá, which is an Argentinian from Cordoba, and also actually Raquel Melgar, which is a really young student. She is now in Bordeaux, but she's related to our department. So I wanted just to remark these kind of things. First of all, Laurent series, okay? So we're working with coefficients, which could be integer, rational, or reals in the main cases. And just we are interested just in the Laurent series, which will be just combinations with coefficients of powers t to the power m, where m is a multi-index, which integer coefficients may be negative or positive or zero. So this is represented here by L hat, okay? And of course, among the power series, there is the polynomial, Laurent polynomials, and also there is a power series, just really with only exponents which are non-negative, and of course polynomials. So they will have like 4 objects, P polynomials, L Laurent polynomials, S power series, all of them are rings, but L hat, which are the Laurent series, is an L module. It's not a ring because it's not always possible to multiply elements. Okay, and this torsion is this structural model is interesting because has torsion. Well, among the Laurent power series, there is here is called RL, which is, I call this rational Laurent series, which are just the Laurent power series for which there exists a polynomial G and just another polynomial F, G different from 0, such that G times S is equal to F, okay? And this is a L submodule, okay? And there is a map here, I call this map a Brion map, which is associated to every, is an L module map, which associates to any rational Laurent power series just an element of the field of quotients of the polynomials and Laurent polynomials, which is just the same. Could be Q of t or R of t, depends on the field or ring we consider for coefficients. Okay, so this map is defined like this. A map associated to such a series is just this quotient, and this is well defined. Okay, and this is interesting because this map has a kernel which is big. I mean, the prototype of Laurent series could be, for instance, to give an example, could be the monomial indicator of any set in the Euclidean space, which is just the summation of the lattice points which are in X, and the monomial t to the power m, which means that. And if one takes, for instance, all the Euclidean space, just the L, the indicator is just the sum, and the sums, you see, the square doesn't exist. This is one example in which one see that we have not multiplication in the Laurent power series, but we have a torsion. For instance, for any variable tg minus 1 times L, for this particular L is obviously equals to 0. Okay, and just this is, for instance, to complete the sample of indicators, there is the polyhedra. I mean, lattice polyhedra. So it's a polyhedra with vertex which are lattice points, and just for this there is several formulas. For instance, I mentioned here Brion, but there is also Barchenko formulas for more or less the same kind of problems, and just this Brion associated to the indicator of the polyhedra is just the summation extended to all vertex of the polyhedra t to the power b, and just the Brion function associated to the indicator of the tangent cone. I mean the f cone. F cone means all the direction tangents to the cone, which is a vector cone. And you have this equality. This means that in order to compute the Brion formula, Brion function for polyhedra, it will be enough to consider just cones, vector cones. I mean, vector means that the only vertex is the origin. And just, of course, here we have in this formula, we have that B is equal to 0 for some polyhedra. This happens very often. If and only if X contains at least one line, or if and only if the set of vertex is empty, so that there is no vertex. In that case, of course, the right-hand side is 0, and of course the left-hand side should be 0 too. Okay. So the computation of via this kind of formulas, the computation of B of indicators is reduced to the computation of B of indicators of cones, moreover, because of the we're focusing in vertices, which are strongly convex. I mean, k into k is the cone, minus k is equal to 0. Okay. For cones, there is many possibilities to get formulas for computing B. For instance, if the cone, this vector cone is simplicial, and U1, U are lattice points of the arrows, just is one considers the fundamental domain, then the B is equal to that, and in general, if the cone is not simplicial, can be decomposed into simplicial cones. Okay. Now let me pass to talk a little bit on Poincaré series. Just our Poincaré series are related to multi-index filtration. Multi-index filtration is something expressed here just in marked in red. I mean, it's just for a ring, any ring R, commutative in our discussions, just take a collection of ideals, indexes by all the lattice points, I mean, with negative coordinates too, such that has this property. G of B is the same that the sup of B0, I mean, the order here means the component-wise order, okay? So this happens for all B. This is decreasing in the sense that for one index which is bigger than other components-wise, the corresponding ideal is a contained thing. The association to the 0 is all the ring. And of course, there is finitude properties. For instance, we can consider this one, okay? So the length is defined when it is defined, or the complement is just finite. So this allows to define the Laurent-Herbes power series, which will be the summation of these lengths times t to the power b. This is a Laurent power series because takes also the negative part. This is L. This is something similar. I mean, here one is considering just the quotients g of b times g of b plus 1. This one means all components equals to 1 is a vector. It's a multi-index, sorry. And just we have here this L, and the Poincaré series can be defined either of this way or this one, which are of course equivalent, is multiplying times this polynomial. We get already a power series, and then this t to the power minus 1, this t is the product t1 to tr, okay? We can perform this, and we get always a power series, which is the Poincaré series. The same happens if we use the function L, which is just the same. Here we get already a power series, and we have here the power series t minus 1, which is invertible as power series, so it allows to create an element which is the power series p, okay? Well, the case more used for us, because we are concentrated always, all time, in singularity theory, are the so-called valuative filtrations. So this just means technically that they have this property. I mean, the intersection of two of the g's is just g of the sup, component-wise, okay? This is equivalent to the system of R functions as many as variables, such that the ideal GB is the intersection of the classically called valuation rings. So it's the set of H's such that the order function in H is bigger or equal than BG, okay, for every B here. An order function is, I mean, which is necessary is only that, is a map from theta, from R to theta to union to infinity, such that the origin is the evaluation, the order function in the origin is infinity, and 1 is 0, and for the summations they have these properties, and it has this property too. The last one is the condition necessary, and the last two necessary for guarantee that GB are ideals. I mean, if you have order functions, you have a relative filtration and conversion. Okay, is elementary. When you have this particular situation of evaluative filtrations, we have also fibers. Okay, fibers, it means just for every multi-index B is the set of functions as that the order functions are exactly equal to Bg here. This is not a vector space in general for more than one variable in general. But when in the geometric situation, one is considering algebras over C, for instance, the local algebras of singularities. This FV is a vector space, rather big, but there is the corresponding action of C star, which left stable to the fiber, okay, because of this property V of 1 is equal to 0, and the others combined make a C star action, and we have the projectivization and the Euler characteristic when it's existing is possible to, and this happens in practice with frequency. Okay, this allows to consider for expressing the Poincaré series now in a more visual way. I mean, more conceptual way, which is on one hand just the generative function of those Euler characteristics, and on the other hand an integral with respect to the characteristic Euler characteristic. Okay, which can be defined for that and discussed. Okay, this integral mainly it was important to compute the many Poincaré series because sometimes the spaces are big, but there is big pieces which can be deleted because they didn't contribute to the characteristic of the Euler characteristic. Okay, this becomes a powerful technique. Okay, for instance, the more paradigmatic result, Felix Delgado was also mentioned yesterday. Just is the plane curve singularities when one is taking the order functions given by, or valuations directly, given by the vanishing along the branches. So for that is necessary to take parameterizations of the branches and take the order of the parameters in the substitutions, corresponding substitution as explaining now in the screen. Okay. So one is taking the minimal resolution. Okay, one can take those exceptional divisors, and for each one of them can take the complement of the intersection of this divisor with all the others components, and this space appear here and appear also in the computation of the Poincaré series. So this kind of result is repeated in many similar to this in many other computations in many other cases. For instance, in the talk by Felix yesterday appear in the actual results, in the current results appear formulas like this. Frequently even with an alternating product of this kind of cyclotomic terms. Okay. For normal surface singularities, the situation is similar because now we can take the minimal resolution of the surface singularity, and we have also divisors. We have now is the vanishing not along the branches. This is a kind of valuation used for curves. Now is just for surfaces. Is the vanishing along the sectional divisors, the components of the sectional divisor. From that, it is create a filtration. Now we have again a Poincaré series. Poincaré series is a power series, but it's not in general a polynomial, nor this. It is a polynomial in the case of curves. I forgot to say before, but the formula is still in the screen before. But just the components here allow also to understand the singularity, and for that we have the intersection matrix or equivalent the dual graph of the singularities. The Poincaré series determines the genus of the components, which are curves in this case, and determines also the intersection. I mean the intersection matrix of the components, but not conversely. I mean, there is in principle in Px there is more information, and in general we can say that Px is not in general a polynomial, could be a power series. And then on the nature of this power series, really I don't know so much. Okay, it's something to need to be discussed. Okay. Now there is the particular case of rational surface singularities. Here is our paper also with Felix and Sabir. And just here, there is many ways to express this, but in this case, the Poincaré series is a rational function. I mean, it's a quotient of a polynomial times the some denominator. Okay, and it can be expressed in many ways. For instance, in our Invenciones paper, there is this formula in the top, which means that can be discussed directly. Okay, other case is the case of also evaluative filtrations, is the affine toric varieties. Okay, this kind, now we are focusing in, as before, in rational strongly convex vector cones. Okay, this again represented by K, and here we have the lattice points inside the cone is a semigroup Sk. So here the ring should be the ring of the semigroup. I mean, is the algebra, the minimal subalgebra of the polynomial algebra containing t to the power m for all m's in the semigroup. Okay, here the more natural valuations are not taking to do with the resolution, but take to do with just the toric parameters. I mean, here, for instance, for taking the valuation of the ordinary functions, one takes elements WB1, WBR, which are in minus the interior of the polar cone. Okay, polar or dual. There is two names for cones are the same thing, the same object. Okay, so for these vectors, because the inner product of the G times 2x is negative, there is a minus here. This means that they define valuations. I mean, monomial valuations or on the ring R. Okay, and so there is a filtration and evaluative filtration, and there is also a Poincaré series. In that case, the Poincaré series is related to the indicator polynomial. Just this formula. This means that okay, if one has chosen the order functions are those vectors WB1, WBR, and we have this map to any lattice points. One can associate this. This extends to a map, a polynomial map of this type. U to the power m is t to the power this second term. Okay, and now the Poincaré series is just the image of the lattice indicator. Okay, of the cone. In particular, this polynomial is this Poincaré series is just a rational Laurent So the Brion map gives for it these formulas like this. Here, for every m in the semigroup, one define a simplicial complex, and this simplicial complex appears here if the set E considered fixed at the beginning is generated in the cone. I mean, contains at least one element in every one of the arrows of the cone, of the edges of the cone. This provides this nice formula which explains that the term upstairs is a polynomial because of this condition of finiteness, and the denominator is of this type. Okay. So we have precise formulas also for B of P. P is a rational. And this can be discussed like this. But besides the evaluation filtrations, there is other many filtrations, of course, and are also interesting. Yeah, and I can say that the first idea to study this came from Sabir and Evelyn. Okay, but the idea is now imagine that your ring is A quotient to an ideal G, any ideal G. And here one can consider evaluative filtrations just on the ring A. And then there is a filtration also in R induced by the filtration here. The multiindex filtration of A is given, but now provides more filtrations just on R of this type, for instance. It's easy now just to take the summation of all the ideals of the first filtration times G, and this is not an ideal on R, but of course there is aviation with all the ideals in R which are of this type. Okay, this is the induced multi-index filtration. Okay, and this has also many applications, mainly because for instance, if one is taken on A, so if one is taking on A evaluative filtration, and we have, for instance, valuations centered in the A could be a local ring, H an element, R the corresponding ring modulo H, and one can take the induced filtration, but by the filtration of valuations centered in the maximal idea of A. And one has always this formula. Here is not erased, but this formula is alive. I mean, P to the power R is T to the power to Q minus 1 times P to the power I. In many of our computations at the level of A, I mean, at the level of considering divisorial evaluations, curves, and so on, this is a product of cyclotomic terms. Here there appears one more which depends of this H, and this allows also to use induction and so on. So this Q is just the value of one H times value R times H. Okay. Okay. Here, for instance, one of the applications of that is, imagine you take now a curve singularity given by an equation H, and imagine that you take consider the embedding. A should be the ring of the plane. I mean, and just imagine you have the resolution, and just the resolution. Imagine there is the only every divisor has only one branch transversal at the resolution, or no one of them. I mean, and you take the evaluations corresponding to the branches. Okay, And this gives a filtration on the plane, but this filtration on the plane is induced to a filtration of the curve. And again, happens that the Poincaré series of this induced filtration determines that it is determined by the topology of the curve singularity. By the way, this happens also, I forget to say, for the case of the Poincaré series of the own curve, okay, mentioned before. Well, other application. This is in combinatorics. Okay, I just the study of matroids. Okay, just in this case, I mean, for matroids, one can understand either as linear matroids here. I mean, representable matroids by the way. Just one consider just all the a finite set of vectors. This could be a good definition of linear matroids, but this is equivalent to say that if you have here in combinatorics, it's necessary to fix the basis of the vector space. So one happens that it happens that one has the vector space and just the fixed coordinates, which this means that in particular, for instance, you have linear spaces, and these linear spaces are exactly the matroids, which are related in many different ways with respect to the edges. And also one has the curve C, which is just the union of the coordinate lines, okay? And here, every subset of vectors has, of course, a rank and has a nullity. Nullity is just the intersection of this subspace with the coordinate space, which corresponds to the index of those vectors. Okay, and one can consider here this ni, which is the summation of all the monomials, which correspond to nullity I. I mean, considering all the subsets of the set of index of the vectors such that the nullity is equal exactly to I. You can see that these computations here are free of the squares. So this means that this is why I'm using the notation sigma, because this means that are subsets of the set 1 to n. Well, here over this ring, which is the ring of polynomials, there is over this ring there is several objects. I mean, on one hand, this I call universal filtration. This filtration, this is not at all, it's just very far to be a evaluative filtration, okay? It's just given by these ideals for every B, okay? And one has also the ideal of the curve, okay? The curve is the union of the edges, coordinate edges, so having those equations. And just the matroid gives the subspace M. It's a linear subspace of our corresponding space. And so over this quotient, the universal filtration gives rise to an induced filtration here. Paradoxically, this induced filtration is more close to evaluative than the original one. But it's only for every matroid. You have only one object that's independent on the matroid, and the matroid disappears here. So if you make this vector space M to run over all possibilities, you get many evaluations here. Well, the Poincaré series of this object is just the same, has the same information than the nullities, and just the nullities has the same information that the usual parameters of the matroid, for instance, the Whitney polynomial. It's a polynomial in two variables, collecting the ranks and the nullities of all the elements of the matroid. Okay, so now let me consider the following. When one has, for instance, one Poincaré series or other object, the linear indicator of polyhedra and other things, just usually just the coordinates T1 to Tr can be substituted by the exponent, the logarithmic coordinates. I mean, one can take other set on the same number of coordinates and just take this change, which means change in every variable. So the idea of that is just usually in coordinate T, the expansions which one could need are just in the point 1, 1, 1, 1. I mean, but if you take logarithmic, this in the y's, the corresponding point is 0. Okay, so this is of course not always possible, but so one possibility is just to consider here I mean, I consider all the power series for which the power series in the variables t, for which the convergence radius is bigger than 1. This means that it's real, but this means that this means that f is convergent is some multi-interval product of minus rho times rho, but itself several times, but just with rho bigger than 1 in order to have convergence in the neighborhood of the point 1, 1, 1. Okay, and one can consider this T, which is a multiplicatively closed set, which is all those expressions which appear frequently in the denominators of our computation of series in several contexts. Okay, and one can take the localization of D localized in T, which is just this space. Okay, in parallel, one can consider in the variables y, we have here several rings. I will mention the polynomial ring, the ring of entire functions, I mean functions which are analytic on all the Euclidean space. Here there is the convergent power series, and here the formal power series. Okay, for all these spaces, I mean, what happens is one can consider also just another multiplicative set, which is a subset of polynomials, and it's just this set is just the product of linear forms. I mean, M is the product of linear forms in the variables y's. Okay, so this means that a typical element on the bigger all of these localizations, so the formal power series, is of this type, and there is an analytical expansion of this type. The denominator is a product of lines, so it's a homogeneous polynomial in particular, and so if you have a power series, you can decompose into summation of components, divided by q, you get the components of this new. Of course, the S and Q depends on are not uniquely determined, but by the rational functions which appear on the right, all the summands, they are so okay. So this in particular will have an order for one expansion at that time. I will call this graded analytical expansion, and this is typical in the literature, classical literature, appear very often. Okay, so one have this, and just the main model I call this theorem in order to focalize in something concrete. So the exponential change is a well-defined map lambda from the localization of T, those functions are convergent in the neighborhood of 1 in the variables T, are the convergent power series localizes in M, which is the set of product of linear forms. Okay, and just the lambda is defined like this. Is writing in the screen now. Okay, so F is in F we can substitute because it's convergent in the neighborhood of 1, and you get an analytic function like that after substitution. This n in the denominator appears here, this type, and here those terms are, of course, taking these linear forms, and just the complement, which should be this one, appear in the denominator now to the power -1. Of course, this product is just by definition the Taylor expansion of the corresponding dot series, which has components which are the dot polynomials. Okay. We have also Brion type maps. This means that here we are controlling the denominator only in T, so essentially product of monomials times cyclotomic terms. Okay, and we can discuss spaces in which F is, in the first case of the three, F is allowed to be is asked to be a polynomial, but here could be an integral function, and here could be a convergent in the neighborhood of 1 function. Okay, and you will have all this space, and we have well-defined Brion type formula. It's the same than before, and we can make the combination of the exponential change, which is lambda, times this Brion type map, and we can go directly from here to to all formal power series for which exists an element in type, a polynomial here, and a function converging in the neighborhood of 1, and just the image is analytical expansion. Okay, roughly speaking. So this is elementary, but this is just for instance, if we came back to the case of monomial indicators, of course we have this, and just the analytical expansion we have this, because in this case the X is a rational Laurent series. And we have the Brion formula, explain it again here, but the analytical expansion has, in that case, is interesting because this formula on the right there is cons. This cons has degree negative, -r. In fact, if r is the ambient, but the summation is in case X is a polytoph, for instance. The summation makes disappear all the terms in the negative side cancel, okay, in the summation, and appears the way to count analytically the number of points inside a polytoph, which is just the value of the origin. We need to, the many terms disappear except the independent term, and this independent term is an integer number, which is the number of lattice points. Okay. So now, in my opinion, one challenge is to be developed. Is just to consider what happens with Poincaré series. How long is possible to perform the exponential change? The exponential change here is lambda b, and in the formulas which now appear. Okay, and so if the Poincaré series belongs to D, localizes in T, okay, this is equivalent to the Laurent Hilbert or Laurent L, one or the other here are both together, but this is an equivalence here too, in the middle, okay? It belongs to this space. So Px belongs to this space if and only if all of this belongs to the same space, okay? In case that P, particular case in Px is already convergent in the neighborhood of 1, okay, we have formulas of this type. In the general case, this is more complicated. And this is what appears, and this corresponds to the original definition. The orders are more or less controlled, and we have this. And let me to finish, if I have 1 minute more, to say that my opinion is that maybe it's important to mix all these techniques in one sample another, and try to see how long we get more applications still of Poincaré series. There is another object, which is the volume of polyhedra, also classical. Okay, if one has a polyhedra, zeta could be just the polytope generated by the vertex set, and k the recession cone, and one can define the volume of X, which is not in general, of course, a number, it's a function. It's a function of the variables Y directly. So here we don't have variables T, but we have variables Y. Are defined like this, well defined unless over the polar cone, or dual cone, okay? And we have an analytical expansion. This analytical expansion, when X is a polytope, in general, there is a baryon formula too. And when X is a polytope, just in that case, all terms in the negative side cancel. Only is preserved the independent term, which is of degree 0, so it's a number. And this number is the Euclidean volume of X. This, I mean, for instance, in the literature, both, the cases, the volumes and the interlattice points are combined because there is the formulas, for instance, by Berlin and Verne, which compute volumes in terms of points in the faces of the polyhedra, considering all the faces, of course. So thank you very much. I finish here.
Thank you, Professor Campillo, for this beautiful talk. Are there any questions?
So you discussed something about approach to matroids. I didn't catch whether this gives new invariants of matroids or simply another expression for known invariants.
Thank you, Sabir. I think, the invariants which appear are the usual ones which appear in the formula. So I computed the Poincaré series, okay, and the result which appear in the way I expressed before is the more comfortable for me, but there is alternatives which are equivalent. But the invariants there are the usual invariants. But maybe you pose a nice question, how to express this, and maybe take as interesting all possible invariants which are maybe hiding in this computation and maybe are more interesting and could be applied to matroids. Of course, this will be a nice product.
Thank you. More questions to Professor Campillo. Okay, then let's thank the speaker again.
Okay, thank you very much.
And now we take a pause for lunch. Please follow the first floor, the dining room. Yeah, thank you.
Mm-hmm. Please enjoy in the lunch. I will go to take my coffee also to our cafeteria. Yes, thank you very much.
Thank you.
And congratulations, Sabir.